back, students. Now today we'll discuss about clearance and clearance volume. Before we go to the clearance and clearance volume, already we have some idea about reciprocating compressor and different types of compression process. That is basically polytropic process, isentropic, and as well as adiabatic process, or it is also sometimes called isentropic process. So now today's class will be on clearance and clearance volume. So this term is very much new to you, that clearance and clearance volume. Now you already have some idea. This is a piston cylinder assembly, you know that, and this is the suction valve, and this is the discharge valve or delivery valve. Now this is the piston cylinder assembly in which pistons can move from up and down, or you can say that from top dead center to bottom dead centers. So the piston can travel from top dead center to bottom dead center only, but there is some gap actually when pistons moves from up to down or from top to bottom. There is some gap in between top dead center and the cylinder head. Top dead center and cylinder head. So these portions, so this one, so this is the top dead center. Piston can moves down and up to bottom dead center, and pistons can move up to top dead centers. It cannot reach up to that point. Okay, so top dead center. So there is some gap actually, and that is basically called or dead space. You can say that the gap or dead space that is basically called clearance. Okay, in a piston cylinder assembly, when pistons can move from top dead center to bottom dead center, so there is some gap. It is given to you that gap because of, so there is no vibration at all, and there is actually no damage at all. That's why it is given in the piston cylinder assembly. So, and there is some gap, or you can say that some dead space are there in between top dead center to the cylinder head. Now this space actually is known as clearance, and obviously so clearance volume and clearance actually designated with capital C term, and the volume occupied within this space is actually known as clearance volume. That is nothing but capital B small c. Now if you draw the PV diagram, of a compression process or in a compressor, so what you see that any piston cylinder assembly, there are basically 4 stages or 4 processes are there. Now 1 to 2, you know that is the basically process where the compression process takes place, and 3 to 4 is the expansion process takes place. Okay, now when you have to consider that you know that 1 to 2 is basically a diagram in the process PV diagram that actually expressed as a compression process, and 3 to 4 is your expansion process. Okay, now in a PV diagram, what you see that V1, so 1 point here, so this is the PV diagram, so this is the 0 initial point. Now this is point 1. Now from 0 to 1, that total volume, that is basically V1 from 0 to 1. So that volume is corresponding to point 1, that is called V1. So from 0 to V1, so from 0 to 1, the corresponding volume is V1. So total volume in that case, in this case actually, that is V1. Now from V1 to V4 or V4 to V1, the gap, the distance, the volume, that is basically called effective swept volume. So that is basically nothing but V1 minus V4. So this is V1 and this is V4. So V1 minus V4, actually this portion of this is, that is actually called effective swept volume. So that is V1 minus V4. Now actual swept volume is V1 minus V3. V1 minus V3, that is your swept volume. Swept volume generally designated with V suffix S. So that is swept volume. Now the gap between the top dead center and the cylinder assembly is basically designated with VC. That is basically clearance volume. Now that point, so 3 point corresponding to 0 point, that indicates your clearance volume. So the total volume, so V1, we can say that, or we can write down. So total volume V1, so total volume V1 is nothing but summation of sweet volume plus clearance volume, right? So this is V1, now this is 0, this is V3, or V3 sometimes it is called VC. So total V1 is equal to VC plus Vs, means clearance volume, plus sweet volume. And sometimes sweet volume is also called piston displacement volume. Piston displacement volume. Sometimes it is also called piston displacement volume. Okay. Now if we consider, actually in previous class, when you calculate the work done required or power required for different compression processes, we are actually just consider, so there is no clearance at all, because this is basically ideal reciprocating compressor. But in that case, actually in this case, we are considered that there are some clearance gap, some clearance actually given the piston cylinder assembly. If it is supposed so, then what is the power required for that case? Now you have to calculate. Okay. So we know that actually, so this is your diagram. Now suppose, assuming that 1 to 2 is your compression process, from the diagram, PP diagram, just write down it. 1 to 2 is your compression process, and 3 to 4 is your expansion process. That both the process follows that polytropic process, that is nothing but P to the power n is equal to constant. Now what is the work done required for that? In that case, actually, what is the work done required? When you do calculate work done required for that cycle or per cycle, first you have to calculate the work done required for total cycle. That is basically, so 1 2 3 6 5 4 1 minus, because you have to calculate this amount of work done. What is the work done required for per cycle is nothing but this portion, right? Now when you calculate, first if you calculate the work done required for the cycle 1 2 3 6 3 6 5 4 1. Now if you subtract the work done required for this portion only, so that is 36543, 36543, then you can get the work done required for the process 1 2 3 4. If you calculate the total work done for the process 1 2 3 4 6 5 4 1 minus of or subtract this portion only, then you can calculate this work done, this required work done. So that is here. Now what is work done required for cycle? That is W, that is area 1 2 3 6 5 4 1 minus of area 3 6 5 4 3 1. Now that is, you are already aware of that the what is the work done required for the polytropic process if we do not consider the clearance. Now for that case, when you consider that this cycle, that is 1 2 3 6 5 4 1 is a total cycle, so there is no clearance at all. Similarly, when you calculate the work done required for that cycle, so there is no clearance, because the cycle, the total PV diagram is 3 6 5 4 3, so there is no clearance. So when you calculate, that will be n by n minus 1 P1 V1, already we are given P1 B1 into P2 by P1 into the n minus 1 by n minus 1 already. Now from that diagram, you also know that, so is here is a constant pressure line, so you can write down P3 is equal to P2, right? And this is P4 is equal to P1. Now from that point of view, just you replace that. So in terms of P3 is basically is your P2 here, P4 is equal to P1. So both are actually same, and this is nothing but this is your pressure ratio. Now What is the work done required? So just algebraic summation are there. So n by n minus 1 p1. So v1 here, v1 and v4 here. So p1 is usually common, n by n minus 1 p1 is will be common, and v1 minus v4, and remaining portions, so p2 by p1 to the power n minus 1 by n minus 1. So that is kilojoule per cycle. Now in this case, the previous expression was what is the work done required if the clearance volume is not neglected. Now what is the work done required for that case? So n by n minus 1 p1 v1 p2 by p1 n by 1 minus 1 minus 1. So that is kilojoule per cycle, but when we are not consider the clearance in the piston cylinder assembly. So now when you consider that there is some clearance, so that is the difference. Here it is V1, here it is V1. Now in terms of V1, here V1 minus V4. That means this is your effective swept volume. Effective swept volume. So this is the work done required when you do not consider the, when actually they consider the clearance is given in the piston cylinder assembly. This is the work done. Okay. So thank you very much for listening me and watching me. Goodbye.